it means you don't only have one op-amp, you have more than one op-amp. So we'll take some examples and see what the result might look like if we take more than one. So here's my circuit. Leave a little space on the top because I'm going to draw the op-amp is right here. This is minus, this is plus, the plus attached to the ground. And the minus, I'm going to make, well, I'll give them different values for the resistors. So let's take this one. This attached to one resistor, we'll call it R. Has a voltage source here, we'll call it V1. And that voltage source could be AC, could be DC, it doesn't really matter. Just a voltage source, V1. I put an AC one intentionally. So I have another one here. And that's V2. And the value of that resistor is also R. That's going up here. RF. They call it the feedback. That's where the F really came from. Then now we have another op-amp here. Notice the result of this going through another one. We'll call it R sub 1 here, going through R sub 1. Entering another op-amp. And this is minus on the top, plus on the bottom. 0 here. And this is R sub 2. And the question, what is V out? Can you find the expression for V out? So what I'm going to do is relabel these. I'm going to call this Vx. Let's write what we know. There's two assumptions about op-amp we make, which is what? First assumption, in case you forgot, I'll write them down. V plus equals V minus. That's the first assumption. Let's look at the op-amp here. What's V plus right here?
0.
So what's this voltage here?
0.
0. Let's look at this. What's this voltage here?
0.
0. What's that voltage here? 0. The second assumption, the current entering the op-amp from this end, that current, this current, is equal to the current exiting the op-amp from that end. And that's equal to 0. No current will enter the op-amp from this end. Why? Because we make the assumption that op-amp has an infinite resistor there. So that current is 0, this current is 0, this one is 0, that one is 0. So if I make this assumption, I'm in business now. I can find Vx. We can assign current any direction you want. Go ahead. Which way for R? This way. You want it left or right?
Right.
You want it to the right? This one. I'll make it to the left just to be different. You know? I1. I don't want you to think it's always to the right. It will probably be going to the right, but you can make the assumption any way you want to. Same thing right here. Which way you want it to go? Left or right?
Right.
Oh, one said left, one said right. I can make it go up. So maybe with this, I'll make it go to the right. But here, I'll make it go to the left to make you both happy. What about that current here? Oh, I already drew a current going to the right, so I guess I don't have a choice.
Isn't that the same as I3?
I said no, because there could be a current going this way.
Oh.
There is a current that will go down that way. That's not 0. Only this current is 0 in that current. So this current going in is not 0. Why? Because the resistor here is really 0, and you have a dependent source. So that current is not 0. So this plus this, oh, this one coming in leaving, these two are leaving. You know. Let's call these just, so I'll know which one's which. Like this is V1. So when I say K, and we'll call this V2. So when I said KCL at V1, you know what I'm talking about. So let's look at KCL at V1. It says if you take all the current entering that node should equal all the current leaving that node. What is entering that node? I sub 1, and what's leaving? I sub 2 plus I sub 3. Notice I didn't even think which direction the current, just made assumptions. So I sub 1, based on the way I drew it, it's going from here to there. So it's this voltage minus that divided by that resistor. This voltage is V1 minus the 0. Oh, I can't call it V1. That's V1 here too, right? So it's called Vx and Vy. I have Vx? Oh, yes. God. Va and Vb, I guess, huh?
Wait, why can't that be V1?
Because V1 is right here.
Oh.
So I don't want people to get confused. So this is Va. So I want people to know I'm talking about that node. So it's V1 minus 0 divided by R equals I sub 2. I sub 2, I define it exiting that node. So it's this one minus this, 0 minus V2 over R, plus we define I3 go in that direction. So this one minus that. This one is 0 minus Vx divided by Rf. And now I just gotta clean the math. So if I clean the math, I will have V1 over R equals negative V2 over R minus Vx over what? R sub F. What's my LCD here? R times R sub F. So if you multiply, you have V1 R sub F equals negative V2 R sub F minus what? Vx times R. Bring this one to this side. V1 plus V2 times R sub F, if you factor R sub F, equals negative R times Vx. And to solve for Vx, we divide by negative R. So it's a minus V1 plus V2 R sub F over R. I put the minus in the front. Are we good with that one?
We're trying to find VO.
Yes. So now let me show you where we are now. So this is my Vx from this picture here. I don't know if you can see it on the screen. That's Vx. I'm looking at the second one. I have R1 R2. Now I'm looking for V out. And I define my current. If you see them, I labeled them last time. I sub 5 going this way. No reason why I chose going to the left. And I sub 4 is going that direction. No reason. And we call that end VB. And this voltage here is 0. And the current going in, the current coming out is 0. So now KCL at VB. That's right here. The current going in is what? I sub 4 plus I sub 5 equals the current leaving, which is 0. From my picture, I sub 4 is Vx minus 0 over R sub 1. From my picture, I sub 5 is VO minus 0. Oh, that's supposed to be a plus here, right? Over R sub 2. equals 0. That's a plus here. This plus this. LCD here, R1 times RF, or R2. So if I multiply there, that'll be R sub 2 Vx plus R sub 1 V out is equal to 0. R sub 1 V out equals negative R sub 2 Vx, or V out equals negative R sub 2 over R sub 1 times Vx. But wait a minute. What is Vx? Remember what Vx is? Right here. So that's negative R sub 2 over R sub 1 times negative, bless you, V1 plus V2 R sub F over R. Negative times a negative is positive. I'll multiply the resistors on the top, R sub 2 R sub F over R sub 1 R times V1 plus V2. That's what my V out is going to be. You give me the values for them, I'll tell you what they answer.
Could we just remember the way that each of the op-amps?
If you remember that, then yep, you can use them. And if you remember from last class, I put this picture up there. So if you remember what each one does, then you can just make it much faster. And again, that goes back to this. And if you're watching this online on YouTube, freeze your screen, take a picture of this. So that's these here. It gives you the equation for them. That's the last one here in case you can't see it. Again, I'll let it sit for a few minutes here. So if you know what this one, notice that's what we did the first one. Look at the equation. It says this one over there is times the sum of them with the minus sign. So if you knew that, you don't have to do all these equations.
What if all those resistors were different?
Then they got to derive them. Because that equation, when they're all equal. So you still go, this current plus that current equals the current leaving. But now your LCD is not going to be R. It's going to be R sub 1 times R sub 2 times R sub 3 times R sub F. So the logic doesn't change. It just, this will not be the answer if these resistors were different. You got to include each one of these resistors back into the problem. And again, this is the last one here. If the circuit looks like this, it's V2 minus V1. This won't be. But notice with this, we made all the resistors equal. And that goes back to your point. What happens if these resistors are not equal? Then what we did here in this equation does not work. But we derived every one of these last time, so you can look at the derivation on the last video and see how we did the math for them and just change the resistor from R to whatever number they give you. So let me take another one where the values are not equal. Because the book always tries to do them with the values are equal. You're right there. So let me go to the end of the chapter. Maybe I'll find something. I don't want them equal. I don't want them equal. Come on. If not, I'll make my own.
You just agree not to put that on the test or anything, so
Oh, well, I can't guarantee that. I'll put some different values here. Okay, I'm going to put one here. And I'll let you choose the numbers. So which means your guess and my guess, God knows what the answer is going to be. As good as my guess, I guess. Here's my circuit. We'll leave a space high enough because it's going to go right. So this is going to rise a little bit there. And we'll let you choose numbers in a minute. This is V2. I should have put some space there. Let me push that one just, I can fit it probably there, but let me just put a little bit of space. I'm squishing it there. Let me just, here we go. And this is V out. 1, 2, 3, 4, 5, 6. Go ahead, guys, pick some numbers. All these gonna be, we'll use K's for them, just to make my life easy.
What's this one supposed to be doing? This one's the,
We're not sure what this one's gonna be. We're gonna find out.
oh, okay.
So what's
6, just
6 here?
sure.
You know what? Let's just make them with no K's, just because it makes the math cleaner at least a little bit, you know? So 6, what about this?
5.
5, what about that one?
3.
This one? This one?
1, 2.
Okay. So we just made some values here. Just to show you where the math is not going to change. I don't care what the numbers are. Since there's 2 of them, I'm going to label them as, this is V minus V1, because this is number 1 and this is number 2. How's that? This is V1 minus, and this is V1 plus, right? So we know that's op-amp 1. This is op-amp 2. This is what? V2 plus. This is V2 minus. How is that? Does that make sense?
We already have V1 and V2 though.
Oh, yes. I'll change these to A and B here. How is that? Because I'll have V1s already there. So, what else? We know the current going in here is what? 0. The current coming out here, 0. Current going in here, 0. Current coming out here, 0. I already gave you the assumption that this current is 0, that current is 0. So that's assumption 1. Assumption 2, that V1 minus equals V1 plus. And that will not be a 0. Why?
Because there's a voltage source on both sides.
Well, this is not attached to ground, right? So this voltage here is whatever voltage crossed that resistor. And what is that voltage? That would be a voltage division. There's your circuit right here. There's nothing coming in here. So all this current going to go and drop down this way. So it is voltage division. So V plus equals this source, which is VB, times that resistor, which is 5, over the sum of them, which is what? 11. So 511 VB. Which that's the same as V minus. Or V1 minus. Yep. So this voltage here is 5 over 11 VB. Now let's assign current going in. Or out. Which way this one? In or out? I'm going to call it I1. How about this one? Left or right?
Right.
Right? I2 or IY. So let's look at KCL at that node. We'll call this VX. KCL at V1 minus, right here. The current going in, which is I sub x, equals the current leaving, which is I sub y. What is I sub x? It's VA minus this voltage, and that voltage happens to be what? 5 over 11 times what? VB divided by what? 3 equals this current, that's this voltage, minus that. This voltage, which is 5 over 11 VB, minus this voltage, which is Vx, divided by what? 4. Let's multiply by 12 first to get rid of these. Then we'll deal with the 11 later.
Yes.
Vx.
You wrote just X, so it was.
Oh, Vx. Thank you. If I multiply by 12, I will have what? 4 times VA minus 5 over 11 VB equals 3 times 5 over 11 VB minus Vx. 4 VA minus 4 times 5, 20 over 11 VB equals 15 over 11 VB minus 3 Vx. What are we going to do now to get rid of the 11 on the bottom? Multiply everything by what? 11. I don't like fractions. 44 VA minus 20 VB equals 15 VB minus 33, I think, Vx. Can I solve for Vx? So negative 33 Vx equals 44 VA minus, is that 35 now? So what's Vx? If you want to switch the sign, because the minus sign, you can flip these, make it 35 VB minus 44 VA over 33. Notice the minus sign, I switch the signs here. When you divide by minus, it makes that a minus, it makes that a plus. So I did 2 steps in one. So in case you're wondering what happened to the minus sign, I already took care of that. Now we are at stage 2 of that circuit. Let's revisit that circuit now, what it looks like in stage 2. You have a voltage source here of Vx, which is 35 VB minus 44 VA over 33. That's what Vx is going to the plus side of the op-amp. Here we have 1, and here we have what? 2. And this is, we call this is Vx, which happens to be op-amp 2 plus, and that's op-amp 2 minus. And we know these voltages are equal. So V2 positive equals V2 minus, and that's equal to Vx, which is equal to 35 VB minus 44 VA divided by 33. Now let's look at that node. Let's assign current any way you want to. You want it left or right here? Left. We'll call it I sub y. I did y, right? I sub w. This one, left or right?
Right.
Right. I sub z. Let's do KCL at this node. Right at that node. And by the way, you could have more than 2 op-amp. You can have 3, 4, 5 of them. Just keep going like this. We know KCL at V2 minus, right here. What's the current going in? 0. What's the current leaving? IW and I sub Z. They're both leaving. What's IW equal? This voltage minus this one. This voltage is Vx. So Vx minus 0 over 1. I sub Z is going that way, so it's Vx minus V out over 2. Let's multiply by 2. So 0 equals what? 2Vx plus Vx minus V out. What is V out equal to? 3Vx, is it? And we know what Vx is. So that's 3 times. Let's write what Vx. I have the answer from before. 35 VB.
Can't you just reduce the 33?
Well, that's what I'm going to do. Right? That would make it 11. By 3, this is 1 by 3, that's 11. And that's what V out is. So notice it really doesn't matter what values we use for R. The reason they make them the same, it makes the math easier. If I didn't have numbers, if I had R1, R2, R3, R4, R5, R6, the math does get ugly because of the algebra. But if you have real numbers like 5, 7, 9, 12, who cares what the values are, especially if you're using a calculator. Like I'm using fraction. I could have made the math even easier by using the calculator there. Whatever these numbers are, 35 divided by 11, I just go to that and get that number, VB minus, that's 4. Just a little bit over 3, that's a little 4. Almost 3 VB minus 4 VA. Because 35 by 11, well, 33 by 11 is 3. So that's a little bit more than 3. Maybe 3.1 VB minus 4 VA. So it will not be exactly addition, subtraction. It will be some, smaller value, larger value. Depends on the VR1, R2, R3, whatever we're using for values.
This is supposed to be the voltage minus.
Well, we call them subtractor because it takes the difference between them, yes. It takes VB minus VA in this case, if you want to call it subtractor. If it was adding them, we'll call an adder there.
So the first side was a subtractor, and the second side was a non-inverting amplifier?
The one we just did was the subtractor.
The first one actually subtracted the values for you. This one does not, notice doesn't change the sign. It still have there. Yeah. Non-inverting amplifier, if you look at them, if you want to go the terminology. Where'd you go? Right here. Notice this one, the first one, negative R sub F over R sub 1, so that's an inverting because you get the minus sign, inverting amplifier. This one, V out equals 1 plus R sub F over R sub 1, so it does not flip, that's non-inverting amplifier. Now if you look at this one, V out equals V in. That's a voltage follower. Your voltage here is the same as this one. This one, notice you adding them. And you're also flipping the sign. But they don't care about flipping the sign. If you look at V1 plus V2 plus V3, this is adding these voltage. That's why it's called summing amplifiers. This one is V2 minus V1. We call that subtractor or difference amplifier. So this one adds the voltages. We don't care if it's invert them. Add them and invert them the way it is here. But the fact that it adds them, we call them a summing amplifier. and this one gives you the difference. That's a subtractor or a difference amplifier. Yeah. This wouldn't cover that Zener diodes now. We used to cover that in a class called Digital Logic 2, but a lot of schools dropped that course for the first 2 years, and so we did the same thing. As I said, with all these amplifiers, the assumption that we're making, which is a big assumption, but really when you go to the lab and test them, you will see not much of a difference. In the lab, you don't have ideal amplifiers. You will never get them, because we look at the amplifier like this. If I show you a picture of it like inside, enlarged there. Is that a big amplifier? I mean op-amp. There we go. The reason we say V plus equals V minus, again, if this is the plus and this is the minus, that's the plus, and this is the minus, we make the assumption that resistor, R input, is infinite. And if it's infinite, there is no current going through. That's an open circuit. That's why we said the current going in is 0 and the current coming out is 0, because you have a hole there. Infinite resistor means forget it. It's not going to go through it. It's not going to be infinite when you go to the lab. That's going to be, I don't know, 10 meg. But instead of having this one and this one being the same, it might be 0.0001. So your assumption is still not far off. The other assumption we make when you look at V out, which is right here, the other assumption that this resistor R sub O out will call 0. Again, are you going to have a 0? No. Even if you put a wire there, it's not going to be a 0. And this voltage here, plus to minus, is going to be some number, A or G, sometimes they use G for gain, which is V plus minus V minus, the difference between them. So we know this is not going to be 0. It might be 0.0001, but A, usually it's a big number. Sometimes between 10 to the 3, which is a small value, to almost 10 to the 6, 10 to the 7, a really big number, you know? So if you get A to be 10 to the 4, that's 10,000. Even if that voltage is 0.0001 times 10,000, what are you going to have? You'll have a 10 volts. So these are the two assumptions, that this is infinite and that's 0. Notice the current this way, I never said that current is 0. This current. We never said that. There will be a current going down this way. Or it might be going that way. Depends on what we have. But the current here, the only current we say 0, that's this one, that one, because that's infinite. And V out, we said it's going to be what? We didn't even discuss this one. I'm just saying, let's just call it V out. And based on that, we'll figure that is. But that's really how we treat when we said ideal op-amp, that this one 0, that one infinite. Rn is infinite. R sub O is equal to 0, ideally. And again, good luck getting that. So you might get R sub O being 0.5 ohms here. You might get R sub N in the lab 10 meg. That's not bad. You might get this to be 0.5 ohm. That's not bad. If you did the actual math versus the approximation, we treat them as an ideal op-amp, you will notice not much of a difference between the two of them. So instead of V out being, for example, 12 volts, it might be 11.92 volts. A hair, small value difference between them. So it's not worth going through all this extra math for that 0.01 or 0.05 volt there for V out. Okay.